Hello, viewers. This is Amrik Sen from Thapar Institute, Patiala. Today, we will be learning about complex numbers and their applications. So, let us get started. Before we can define complex numbers, we must know what is iota, which is regarded as the quintessential complex number. Well, from high school, I suppose you recall that iota is square root of -1. But the important question here is, what is the meaning of square root of -1? There are, in fact, two interpretations of iota, and thereby the geometrical meaning of square root of -1. The first interpretation is that iota is a 90-degree rotor, or a rotation of pi/2. Let us see why that is the case. Think about an object which is of unit magnitude. So let us consider the number 1. When we hit this number 1 by iota, we get an iota, right? And here by hitting, I mean when iota acts upon this number 1, it results in an iota. When we act upon this resulting iota by another iota, we get iota square, which we know is -1, right? So let's pause and think about what exactly happened here. We went from 1 by 2 successive application of iota to -1, which is, you can think of as a 180-degree rotation from 1 to -1. So if two successive rotations or two successive applications of iota results in a 180-degree rotation, one can imagine that iota by itself corresponds to a 90-degree rotation, which is why the geometrical meaning of iota is a 90-degree rotor. The second interpretation of iota is that of a bivector. To see that, let's think about a general entity C in an appropriate two-dimensional Clifford vector space. Now, you don't have to know what is Clifford in this context, but it is some vector space, two-dimensional. That entity C can be written as a sum of 4 quantities: a scalar C1, a vector which itself is a sum of 2 vectors, E1 plus E2, and a bivector which is E1, 2. Of course, in this case, each of the quantities can be scaled by an appropriate coefficient, and hence the C sub 1, C sub 2, C sub 3, and C sub 4. This is a general entity in the Clifford vector space. The bivector entity, E1, 2, is nothing but the wedge product between two vectors, E1 and E2, where E1 and E2 are the basis of the two-dimensional Euclidean space. And it turns out that this wedge product is nothing but iota. So in that case, what is a complex number? Well, if you look at C carefully here, you see that the second and the third terms on the right-hand side of this expression constitutes a vector. And the remaining terms, which is the scalar C1 and the bivector term C4E12, can be added together, and that comprises of a complex number, which now becomes clear is the sum of a scalar and a bivector. So these are the two geometrical meanings of iota. Now, where do we see complex numbers in real life? Actually, you see them in many applications. And here I have taken a very particular example, that of a very simple electrical circuit, which comprises here of a battery and a light bulb. You can think of a light bulb as an inductor, okay, an ideal inductor. Because the battery is charged, there is a voltage drop across the two leads of the battery, which drives the flow of electrons. And hence, we say that current flows through the circuit. Now, this system is governed by an equation which is given by the Faraday's law of induction, which simply says that the voltage drop across the light bulb is proportional to the rate of change of current flowing through it. This happens to be a standard law from physics. Now, if we use the complex phasor representation for the current and the voltage, then the current I can be written as a magnitude times exponential of I omega t, where exponential of I omega t by the Euler's identity is a complex number. And likewise, we can write a phasor complex representation for the voltage across the light bulb. When we use these phasor representations, which are complex representations of the current and the voltage, in this equation of the Faraday's law, we recover a very important relation between the current I and the voltage V, which is given here. So the voltage is proportional to iota times I, which is something very interesting, because if you recall what we said in the previous slide, we said that when you hit iota to an object, it turns that object by 90 degrees. Well, in this case, we don't have an object, but we have a waveform which we can see with the help of an oscilloscope. In fact, the output of this particular oscilloscope for this particular circuit is shown here above. So V proportional to iota times I in this case means that we should expect the voltage waveform to be 90 degrees ahead of the current waveform, based on our interpretation for iota, which we saw in our previous slide. And in fact, if we look at the oscilloscope, it turns out that at every point of time, the voltage leads the current by a phase of pi over 2 or 90 degrees, which in some sense means that the voltage waveform in a suitable phasor representation is 90 degrees ahead of the current waveform. So here is an example of application of complex numbers, and its interpretation becomes clear. with the help of an electrical circuit. Now, what are some of the other representations of complex numbers? Well, one may think about the Euclidean plane, the R square, to be isomorphic to the complex plane because C1 plus C4 iota can be written in terms of an ordered pair C1 comma C4. But one must be very careful here. R square is not the same as C because the basis of R square, as we know, is E1 and E2, the unit vectors along the x direction and the y direction. But the basis of C is a scalar and a bivector. And this is a very important distinction between complex numbers and numbers on R square. Now, before we end today's lecture, I want to give you guys a thought exercise as a homework. I want you to come up with an alternative representation of complex numbers in terms of matrices. So anyways, we will come back again next class and discuss further problems using complex numbers. In fact, I will introduce to you the parallelogram law using complex representations, and we will derive a very important inequality which is known as the triangular inequality. So until then, stay tuned and take care of yourself. Bye-bye.